Good morning, everyone. I'm Suarez Riera, and I'm going to present the use of biochar to reduce the carbon footprint of semen-based materials. The present work was divided into five phases, starting with the consideration of semen and sustainability, waste, and their possible option to reduce it, the material usage, and their characterization, results, and finally the conclusions. The semen manufacturing process, from the raw material extraction to the final product, consumes a lot of energy, which translates into a large amount of carbon dioxide emissions. Every year, more than 4,000 million tons of semen are produced, and for each of them, they are consuming 6 gigajoules of energy from fossil fuels and generating 1 ton of carbon dioxide for each ton of semen produced, and contributing to more than 50% of carbon dioxide emission worldwide. To mitigate this situation, various types of material have been studied to obtain semen from other sources or to reduce their impact on the environment, such as the supplementary cementitious material, alternative cementitious materials, and manufactured nanomaterials. Also, other investigations are ongoing in the world. For example, in Mexico, they are using metal fiber production waste to improve the mechanical performance of mortars. Or in Turkey or Canada, they are using alternative energy sources to oil. Regarding the waste, we are in a rather alarming situation. Only in the United States, more than 30% produced food is wasted. This is about 60 million tons. And regarding the wood sector, more than 70 million tons of wood are wasted every year. In the Italian context, about 80 million tons of wood and 3 million tons of wood are wasted every year. What do 80 million food waste means? There is a waste of more than 73 million cubic meters of water, approximately 400 million square meters of wasted land area, and emitting 80 million kilograms of carbon dioxide into the environment. For this situation, biochar can be a solution. And what biochar is? It's a solid material obtained from the thermochemistry conversion of biomass in an oxygen-restricted environment, such as pyrolysis, gasification, and endothermal carbonization. How it used? For usually their application are for optimize the soil properties, the carbon sequestration, environmental remediation, and in the construction world too. It has a lot of benefits such as soil nutrient retentions. It can eliminate organic and inorganic contaminants. It can absorb greenhouse gases such as carbon dioxide or methane, and it can improve the mechanical properties of semen-based material. Why biochar is used in the construction sector? Because it is a porous material. Its porosity is generated by the production process and the temperature reached in this process. In addition, it donates a large surface area to the material, which will subsequently allow a better interaction between the semen matrix and the micro and nanoparticles. This porosity also influences the water absorption capacity. However, thanks to its chemical stability, the water does not react with the biochar. In fact, this water will be released later, helping in the semen infiltration process. This property is quite useful, specifically in areas where high temperatures exist and there is a risk that such a process cannot be carried out completely. Additionally, the biochar has a low thermal conductivity, which implies that it will not suffer changes in its structure during the semen infiltration process. And finally, it helps in improving the mechanical properties since it acts as a shield when it finds a fracture, managing to dissipate it. This happens because it is a material made out from more than 20% of carbon. Portland salmon Taiwan iTech 52.5R, the ionized water, superplasticizer, standard salmon biochar were the material used in this work. In this work, gray Borgotaro biochar was used, produced through gasification at 700 Celsius degrees, using wood chip as a raw material. Specifically, more than 50% of the particles have a dimension between 0 and 8 micrometers, with a surface area of 28 square meters per gram and an average pore of 3.27 nanometers. As said before, porosity gives the material the capacity to retain water. Specifically, gray Borgotaro can absorb 2.17 grams of water per gram of biochar. In this work, the biochar was used as a filler and a substituent of semen powder and mixed in water or in the dry manner with the semen powder. An optimized percentage of 2% of biochar were used, both for semen-based specimens and mortar specimens. Once the maturation and water were finished, a U-shaped cup lid was made in the middle of each specimen, and the three-point bending test was carried out, performing by controlling the crowd mount open display screen and using a strain gauge, with the aim to evaluate the fractional strength and fracture energy. The results in the fractional strength of the semen paste show how the use of biochar mixed in water results in an improvement of more than 50% compared to pure semen. However, in the case where the biochar was mixing with the semen powder, there was a resistance loss of 8%. In the cases where the semen was replaced with the microparticles, there was a resistance loss of 29% and 39% in the cases where biochar was previously mixed in water and with the semen powder respectively. In the case of mortar, it is possible to appreciate how the use of 2% of biochar represents a slight loss of resistance of just 2%. However, when the biochar is fully mixed in the semen powder, the flexural strength drops less than 1%. In the cases where biochar was used as a substitute for semen, there was a slight loss of resistance of only 2% regardless of whether the biochar was mixed with water or semen powder previously. Regarding the fracture energy, the results of semen-based specimens show an improvement of up to 150% compared to pure semen, in the case where the biochar was used mixed in water. The most encouraging results are the cases where the semen was substituted, obtaining more than 108% increase in the case where 2% of biochar was used mixed in water and dry with the dry powder respectively. In the mortars, the graph showed an increase of 37 and 31% compared to the specimens, reference specimens, and in cases where biochar was mixed in water and in dry matter respectively. Respect to the biochar used as a substituent in the mortar mixes, there was a slight increase of 2% when the biochar was mixed with the semen powder and a loss of 6% when it was mixed in the water and superplasticizer solution. From the curve obtained from the three-point bending test, the fragile behavior of pure semen and the influence generated by the presence of biochar in the mixture can be observed. In the case of mortar, the tendency is constant with respect to the semen-based specimens. The increase in the mechanical properties provided by the biochar to the specimens is due to the generation of a more articulated and fracture trajectory, and therefore much less linear than the typical brittle fracture of the cement. This explains the variation in post-break behavior of the material and the increase in the ability to absorb energy before breaking. To conclude, we can say that the use of biochar as a construction material means the recovery of a waste material, and using a waste material implies a reduction in carbon dioxide emissions, thanks to the gasification process. With respect to the semen important paste specimens evaluated, there was a significant increase in fracture energy, which translates into an increase in the ductility of a fragile material. In addition, there was an increase in fractional strength in semen paste and a good performance in cases where the semen was replaced with biochar. In future, further studies should be conducted in exploring the application of biochar from different types of food waste in concrete. Thank you for your attention.